The Cosmic Coffee Bar is open, and with an extra special selection of donuts, hand curated by Helen from the local donut shop, and good coffee. By the way, if the selection of Keurig coffee pods is not to your liking, bring your own pod. You can bring your own pod, and you can even bring your own cup if you like, and no charge for that. But if you'd rather rely on Helen's choices, then go ahead. Okay, we're on now. Let me get in front of the camera. There we go. Oh, we're here. We have 3 cameras hooked up and 4 computers. So it's kind of hard to get all of this organized, but it is now. And so I would like to welcome you both here and virtually to the, let's see, October OCA meeting. We in Hashinger Hall, 369, about 20 to 25 people. And we're ready for an exciting night. There's some interesting announcements you should pay attention to, and an interesting program by Slavik. Where's Slavik? There he is. Okay, so let's get started. By the way, Barbara's not here. They've had some medical things they had to attend to, so she may show up on online, but not on ground. Okay, let's go to the announcements for tonight. Let's see if this actually works. It plays pretty music and it actually works. I'm really impressed. So welcome to the new members. Every month we have a few. Nick Grasau and
you also need to share it for the online audience. We cannot see it. Would you share the screen on Zoom as well, please?
Okay, are we there?
Yes. And
okay.
Indeed, you're brilliant.
Are we on?
We are on all.
Yes, I see a nod. Okay, great. So are those 2 gentlemen here, Nick and David? Squinting, looking at the crowd? Nope. Okay. Cosmic Coffee Corner is up there. Helen is running it. And as I said earlier, coffee and donuts, hand curated by Helen. If you have a particular type of donut you would like to see here, let her know. And if you want to bring your own Keurig coffee pods, go ahead. Then the coffee is free. I don't think she charges for water. And if you want to, bring your own cup as well. Gone are the days when everybody had to drink out of the same coffee urn. Those were tough days. $1 each, located in the library. Okay, star parties this month and special interest groups. Anza Star Party is November 2nd, and the Orange County Star Parties have been off for a while till they got reorganized. Special interest groups are astrophysics. Beginner's class is online. I think that's actually a good opportunity if you're a beginner. You can put your own stuff on the camera and ask questions. Works out really good that way. And then the OCA board meeting is on November 10th, and that will be online as well. All members are allowed and encouraged to show up if you want to see what the business of the club is. Adoptoscope program. We have our own Adoptoscope person here who's going to talk about a new opportunity for you.
Hello, I'm Jake Brown. We are on the slide I haven't seen, but I think it's about the same information I brought. Okay, this is about a raffle we're going to have. It's at next month's general meeting right here at Chapman University here. What we'll be doing, I'm going to read the statement that's going out to next month's newsletter. It reads, raffle of a Meade ETX 125 telescope system. It's a Maxitov Cassegrain design with a go-to hand controller and ETX tripod. Tracking and go-to functions are working. They were tested recently. The scope has been taken from the club's inventory of used telescopes.
Looks like it has a finder on it.
It has, that's not in the write-up, but it does have a Telrad on it and a couple of bubble balances to get it leveled for alignment to the stars. Let me continue with the statement here. The win is on Friday, November 8th, at 7:30 p.m. right here at our general meeting. Participation is open to OCA club members and non-members alike. Interested parties must be present in person at the meeting. Tickets for the raffle are free to those in attendance. And I want to add one anecdote. We're planning a second raffle for the following month, but there'll be more details about that coming up later. So that's good for the raffle.
Okay, let's go over to the lunar scope program. Optoscope program.
All right. This is on the website, and it's looked like this for quite a while. If you click on the download the current inventory.
That's you.
Okay, got it. I don't know if we've got a copy of the current inventory. I doubt that it shows, but if you go to the website, and you don't need to be a member to get into this area, you can click on Adoptoscope and then download the current inventory that's circled in red right there. And it'll come up with the scopes that are currently available for purchase.
Well, if I'm interested in something that's not on the list and I'm curious, can I call you and ask you about it?
You can send me an email.
Email, okay?
At the address is listed there somewhere, scopes at ocastronomers.org. And it will get to me. And that's our program. We do have, I think on another slide, it's going to tell you we've got over 20 scopes. We have go-to types and very simple manual tracking types. They're our complete systems. And they include the telescope, the mount, and the tripod. Some with the tripod, some you need to upgrade. Anyway, that's our program, and I encourage you to look at the inventory. There will be an update coming within a week. So there are more scopes available than you see today.
Good, okay. So now's the time to start thinking about Christmas, eh? Or make it a real Thanksgiving with a new scope and a turkey. That's okay. Yeah.
I do own one. I know what you're talking about. So, no.
I don't think many people are selling their Sea Stars used. They're probably the most in-demand popular scope there is. In fact, I would say if I saw one used, I would wonder how they hurt it. What doesn't work on it, you know? Okay, upcoming events. There's a cosmic art night at Mount Wilson. Mount Wilson is no longer just an observatory. You can go up there and listen to music. You can do all kinds of things. They have a number of events all the time. And for me, just driving up there and breathing the mountain air is pretty good. But the viewing, they have an apparatus like a Naismith tube of some kind that goes down to the bottom of the telescope and out to an eyepiece, and you can put your eyeball on it and see through the 100-inch telescope. I think historically that's pretty cool. And it's a big telescope. You can see some really cool stuff on it. Helen and I were up and looked at it, and we were even on the 60-inch and saw Saturn, and Saturn was about the planet Saturn was about this big, plus the rings besides that. A huge view of something that you normally don't see very much of. So check what's going on with Mount Wilson. Outreach events, Martin Christensen's in charge of that. And there is a pretty good long list of outreach events. So I know you're thinking, well, I'd like to go out there, but I don't know what to do. Good. Go to an outreach event and tag around with somebody, help somebody set up, talk to Martin and help him out, or help organize the line of people. Sometimes there's several hundred people that want to look through the telescopes. Get used to it and see if that's the thing you like. And then next time or the time after that, bring your own telescope. And it doesn't have to be big. What drove me crazy into this hobby was looking through a 60 millimeter refractor and seeing Saturn. And after that, it was all over. You have a question, sir?
The wrong city.
Wrong city.
Cold Springs Elementary School. Wow, that.
So if you're interested in helping out with the outreach, then talk to Martin and he'll give you the right information. Adopt a Scope program. You know, I think we're the only club that does that. And it would have saved me a lot of misspent cash when I was younger. I would have been able to try 4 or 5 different scopes until I found out what I really wanted and know that if I bought one, I would actually use it. And that I came to that in a long route. And I think having the Adopt a Scope program helps everybody out. And at the same time, if you have stuff that's sitting around you won't use again, you could donate it and it would help in the Loaner Scope program. Okay, Dave Fisher is our editor for the newsletter, and he's always looking for observations. If you did anything for the aurora last night, did anybody see aurora last night? Yeah, well, it's kind of tough from Los Angeles, but it was pretty bright in a lot of other places. But if you got aurora pictures or stories, go ahead and submit it. Anything else as well. We deliver the newsletter online and paper copy. If you want to change your method of delivery, go ahead and check at ocastronomers.org and talk to Charlie at ocastronomers.org. Oh, if you're at ANZA and you think you're the last one to leave, check, because we'd like to have the ANZA house locked, because people are there when we're not there, and sometimes that's not a good thing. You want to make sure things are tidy and locked up, and close the gate. If there's somebody else there, they can always open the gate. Weed clearance. I almost don't need to say this. We missed a fire a month ago. This is still fire season, and we need to keep weeds and stuff down. The CAL FIRE I looked up, they said you need to have 5 feet around where you are that's clear. Nothing except gravel. And then 10 feet or 30 feet of no bushes, nothing that would ignite easily. And one of the problems we have is we have great big tall red barked, almost like creosote bushes. If we take them out, it'll just uproot them, it'll affect the drainage and the erosion. But if you cut them way down a foot or two, it won't give any fires that come by any opportunity to burn. And we're actually in a pretty good situation because almost all of our neighbors are clear cut. We're the only ones that aren't. And so there's no place for a fire to get started and move in on us. But if we don't have stuff cut down, two things will happen. It could start on fire. And second, if we're not cleared sufficiently, the fire department won't go in and rescue us. They can't get in and do any good if we're all full of trees and wood. So the more we keep things down on our site, the more defensible it is by the fire department, and the less likely we are to have damage, because no matter how much insurance you have, if we get a bad fire, it'll never cover what we have invested in it. Okay, tonight's moon phase, first quarter, and you can go outside and look at it. There's no marine layer. You can see the moon. It's right out. Anyway, I get excited because I live in Long Beach and we haven't seen anything in the sky for, I don't know, since June or May. Elections are in November and nominations have to be in by the end of the November meeting. And all offices are open. Just talk to Alan at ocastronomers.org if you're interested in running for one of the offices, either trustees or the main officers. Okay. Next meeting will be on November 8th. Those are the announcements, I think, except that we have a presentation by Dr. Slava. He's from JPL and has a very interesting background from somewhere out in the middle of Asiatic Russia. Yeah. Is Kizil. Were you born near Kizil? No, that's too far out. Okay, and then we have Mr. McConaughey to do the what's up. So I think that's the next thing we're going to plug in, right? That's not what I wanted to hear. Okay, Reza, can you see the what's up? Yeah, he's got his thumb up.
Yes.
And now,
all good.
what's up?
Hi, everybody. I came to tell you what's up. So I'm going to start by we're in the wrong section. Here, hang on. Oh, go ahead.
What did you do?
Isn't this what's supposed to be? It's a video recording of some screen. Yeah.
I think that's the first slide.
Sound that pushing out for a second. Okay. No, use the mouse. It's turned off. What do you want to do? It's sharing that.
Hang on a second. I may be able to fake this. Well, you're going to miss my favorite slide. But that's the way it's
Well,
gotta
there
be.
was a play button down below. If you could click on that.
Pardon?
There's what?
If you go to the previous slide, the play button is to the lower left corner.
However, you'll see all the others before I have any chance to talk about them. I hope he doesn't ruin the suspense.
Okay, let me see if I can request remote control to help you out. Can you approve the request? Okay.
Okay. Let's take it from here. People shouldn't have to wait.
Okay, if we click here, I guess we've got the video.
Try it. Try it.
Okay, I failed to. Sorry,
It's
go
not
ahead.
working. This really works on my computer, guys. It really does. There's even some animation here. There's even some animation here. That's okay.
Right.
Thank you. Okay, where are we? Right now, you should be seeing a bus size rock coming in around here from up here someplace, coming in between us and the moon. And as it goes around, it comes out here. We have this little moon temporarily only. It's about as big as a bus and is flying in, will circle the Earth, and it's even closer than inside the orbit of us to the moon. Now, you won't be able to see this because, like I said, it's really small. It's the size of a bus, but a size of a bus at the distance of the moon is still really small. It's going to be about 20-second magnitude, so you won't be able to see it. One other visitor we're going to have that you really should check out if you can is a temporary site. It'll be around till about the end of October, probably. It's Comet C 2023 A3. It becomes visible low in the west following sunset. If the comet's tail is well illuminated by the sunset, you may be able to see it with the unaided eye. Now is the best time to observe it. So get out on a bluff, overlooking the ocean, and point towards sunset. And Venus will be out there. And with your binoculars, see what you can see. Okay, it's worth it if you can see it. And remember, comets are always unpredictable. Now, you have a treat of 3 meteor showers coming up this next month. Unfortunately, meteor showers are best under dark skies. And that nasty old moon's going to be up for most of them. So I'll tell you about them. The Orionids have been advertised as possibly the heaviest meteor shower we'll have this next month. And that's got about 21 meteors per hour. But it's under an 18-day-old moon, which means that at prime meteor viewing time, it'll be light. As with all meteor showers, they're naked eye objects. If you see a really big one and are really quick, then you might be able to try looking at what you saw with binoculars. Meteors are usually gone by the time you can actually get the binoculars up to your eyeballs, but sometimes you can see the afterglow, and that looks kind of cool on a meteor. Meteor watching is mostly lying on your back, looking up with your eyeballs, and just counting them and making fun of your friends and stuff like that. The torids are actually 2 slightly different paths of little grains of sand zipping through the solar system, and then the Earth runs into them. The North Torids comes under a 5-day moon, and then a little while later, the South Torids will have a lot more moon and probably less to see. Although every 40 years, he said, pushing the button again. Yeah. But although every 40 years the Leonids are spectacular, this is not going to be one of those years, folks. A big gibbous moon will be around. And besides that, it's not one of those big 40-year Leonid showers. One other thing in these last 3 slides, you've seen where I put up the stars up there where you can see where the constellation is. You may actually see the meteor any place in the sky. But it's called the Leonids or the Geminids or the Orionids because if you trace the path of the meteor backwards, they all seem to radiate from those constellations. That's how they got their names. Meanwhile, downtown, in the middle of our big little metropolis here, the sun, there's also going to be a lot of action. Solar activity has its ups and downs on about an 11-year cycle. And last year, the solar scientists pretty much projected that right now we would be at the peak. The sun has been showing off more sunspots and been putting out a lot more energy than it usually does. And you can see that as the way the graph grows every 11 years. And we're right up there where it gets really, really high. Of late, we've been seeing more sunspots, and the sunspots have been putting a lot more energy out. Oops, oops. As a result, every week, it seems as of late, we've been getting another internal warning, internet warning that there's going to be a great big storm of particles and energy, and it's going to light up the sky. When the sun puts out more energy, the energy pushes further into the Earth's protective shell of magnetic protection that we have, and the aurora can push further south into the southern area. I want to show you these 4 pictures here. We were out at GMARS last summer sometime, and one of us saw something that looked kind of like this. You know, all those famous pictures you're seeing that look kind of like this, and that? Yeah, you don't see that. Not down here in our aurora. You do up in Alaska, it looks like that. But these 3 pictures, that's an Android and these 2 are Apple, were actually taken by somebody coming out and say, hey, what's that? There was a dull glow north of GMARS. And there is nothing north of GMARS. There's not a whole lot south of GMARS either, but there's nothing north of GMARS. And so as you look up, you see this dull glow and you go, oh, what is it? And so we took our phones out and we just pointed them and said, push. And honestly, that's all it took to get that, and that. This did a little more processing. I got a picture today from one of my buddies who lives up there, and he got a lot more. That's, if you see that, it's not just a haze, folks. That's the aurora. So start working on it, okay? And turn the page. Oh, yeah. You know, from here in the city, you can't see everything that you might like to see, but there are some things you can, and one of those are occultations of the planets and conjunctions of the moon and various planets and things like that. Because planets and the moon are bright enough to make it through the light pollution. This is a pretty good picture. By the way, it was taken with the cell phone, not by me, but somebody else grabbed this picture with the cell phone. And here you can see, or you can almost see, a few of the contacts that you can have over the next month. And you remember, you can see these from the city. Is this movie going? No, this movie is not going because we don't have the right presentation in here. But you can see that Mercury and Venus, is the Earth pointed out there? Earth's up here. So it's on the wrong date too, because the movie's not running. Hi, can we have the lights back on? At least my light. Thank you. Who did that? Anyway, thank you, Lord. This is the inner solar system. And I'm just going to go to the next slide because it's not moving like it should be. And this is the outer solar system. So you can see that the planets are going to be taking this motion around the sky. There are some out there that need to see Pluto. Whenever we talk about planets, we need to see Pluto. And if this whole movie was working, it'd be even cooler. Now, back to reality here. Where are we? Okay, here's where you're going to see the different planets. Mercury and Venus, as I said, are from where the Earth is. Earth's over here, and Mercury and Venus are down here. So you got to look to the west. And on your next big new moon night, Saturday, not the new moon itself, but the Saturday where you'd be out at the deep sky site watching, you can look off to the west right about 6:30 in the evening, and you will see Venus and Mercury, and the moon is just barely set at about 6:30. You might, if you're lucky, even see a comet in there, but it's getting a little late for the comet there. But comets are unpredictable. We never know what they'll do. If you want to see the rest of the planets, though, you're going to have to wait till Mars shakes its butt out of bed. The god of war sleeps late, apparently, and he's not going to get up until about 1:30 in the morning. But at that point, you can look at Mars and Jupiter and Uranus and Neptune and Saturn very easily, and you can see all those planets all at the same time. So that's kind of a cool thing to do when you're out at the dark sky site. But I warn you, you can do that at home too, because all of these things, maybe not Uranus, maybe it's not too easy, but you can pick them out from even light pollution. Now, I've been here before, and I got to take some time because whenever I do a what's up, I've got to tell you about cool things to look at up in the sky because that's what Reza tells me I got to do. So I got to do it. So I kind of run out of ideas for telling you how to find things that are cool to look at. You've heard me talk about Telescopius and all the planning tools it's got where you can find out what's up there. And you've heard me talk about the two favorite, that's star hopping for backyard astronomers and turn left at Orion. Both of those have some cool sections of what things you can look for. You've heard me push you into trying to get into Astronomical League observing lists. They're a really good way to make you a disciplined observer. But you haven't heard me talk about one of the things most of us do most of the time. We just go out there and Google and we ask, hey, Google, what's there cool to see in October? And that's what I did this time. Okay. And you can find all sorts of lists by all sorts of people that are telling you what the best things to see. By the way, the lists don't agree. So that's fun. Okay. So I just took one list and I cut them down a little bit because some of them were really silly. But first thing I had on the first list was NGC 7331. And there's a lot of facts and stuff I got to give you here. So I got to get actually
Off the upper lights and leave them.
you do what you want. I just need to be able to read this.
Helen, turn the upper lights off and leave the blackboard on. They'll be able to see your slides better. Turn the chalkboard back on. Turn this one back on.
Chalkboard back on.
No,
But if I do that, I can't work the computer.
okay, go back to where we were.
There's a way to do this
There we go. Like that.
called, it doesn't have to be that bright, ma'am, called presentation mode. But we can't figure out how to do it here. In which case everything would be a bit smoother, but it ain't. So let's tell you about 7331. It's an unbarred spiral. It's a galaxy located up in Pegasus, about 40 million light years. It's away from us. It's similar in size and structure to the Milky Way. So that's kind of one of our twins out there. And it's got a black hole, supermassive black hole in its center. Visually, it's about a third of the size of the moon. So you can spot it through a 10 by 50 binoculars or 15 by 70 binoculars are cool. And you can actually see stuff and see some of the details in that. But with an 11-inch telescope, you can really see some of the you can't see the color, but you can see the shapes and things like that. But I want to tell you something. That's not what you're going to see through a telescope. Those are photographs. You don't see any color in a deep sky object when you're using your eyeball. There's just not enough energy in the light coming to you from so far away to light up your either your cones or your rods. I forget which one is two colors, but there's just not enough light coming in to light it up. And everything will be just kind of a haze. You can tell the general shape on 7331 because it's fairly bright. On some of the other objects, all you can say is, yeah, there's something there, all right. But that's about all you can do. So if you don't have a camera, you're going to get something like this. If you've got a camera, you may get something like that. By the way, if you have a camera and you're really good. The second object is the Phantom Galaxy. It's a large spiral galaxy in Pisces. It has prominent, well-defined spiral arms You can see them up there, down here, and you could probably pick out a little bit of it. The problem is M74, which is another one of its names, is the second lowest surface brightness object among all the Messier objects. And the pinwheel is a little bit dimmer. And basically, when you look up there, you say, I can't really see anything. And that's about what you see. You know, even with a pretty good telescope, you may not be able to pick out much. You can try this to spot the galaxy with large binoculars, and it'll be just a faint dot of light. But if you use a small telescope, you should be able to get something out of it. The Blue Snowball Nebula in Andromeda. Now, this one's kind of pushing it, guys. You better have a pretty good telescope for this one. It's a planetary nebula, and it's one of the closest to the Earth, about 6,000 light years away. It's an elliptical shape with triple shell structure. So you got some really cool things to see there, although I'm not sure you're going to pick it up in a telescope unless you use some pretty good filtering to try to pull it out. You need at least 160, 150 millimeter, basically a 6-inch telescope, about 100 powers, and you can see it as a slightly bluish disc. 1/100th the size of the moon. NGC 3000, the next one on our list. Something for you to look at. That's kind of cool to go out there and see. So it's a spiral galaxy in Sculptor down south. It's similar to the Milky Way. It looks like us, acts like us. It's about the same size. It's about 6 million light years away from us, though. And it's one of the closest galaxies in the local group. This local group, incidentally, is us, Andromeda, Milky Way, and a few other group of galaxies that fly around through space together. About 2/3 of the apparent size of the moon. So it's getting pretty big here. Under very dark skies, you can see NGC 300 with 10 by 50 binoculars. In an 8-inch telescope, you probably be able to pick out its nebulosity and some of the details in it. The next item on our list is the Sculptor Galaxy. And this one's pretty cool because it's pretty easy to find. You can point it down there in the south. And it's one of the most easily observed galaxies outside of the Andromeda Nebula. It's also called the Silver Coin, the Silver Dollar Galaxy. It's an intermediate spiral located about 11.4 million light years away from Earth. It's the brightest member of the Sculptor group. And as one of the brightest galaxies in the sky, it can be seen through 10 by 50 binoculars as kind of a fuzzy, elongated patch. So you can actually see this with 10 by 50 binoculars, which aren't that big. The Helix Nebula is a planetary nebula, about 655 light years from us. And it is one of the closest planetary nebulas to the Earth. It's got low surface brightness, though, so you can miss it if you don't pay attention to what you're looking for. NGC 7293 is difficult visually. You can try to spot it using 20 by 100 binoculars, but it's really good if you can put an O3 filter or a UHC filter on it. Now we get into some really popular objects. That's M2. M2 is a globular star cluster located about 40,000 light years from Earth in Aquarius. It's one of the brightest clusters visible from the northern sky. And under a perfectly dark sky, the core of M42 can be seen with the naked eye. I've seen it, just, hey, what's that thing up there? That's M42. But 10 by 50 binoculars will bring it out well. Now, I know those of you out there are saying, hey, wait a minute, you've seen one globular cluster, you've seen them all. And there are like 150 in our galaxy and thousands in other places. For those of you who believe that, next slide, please. For those of you who believe globular clusters all look the same, you need to go back and watch the YouTube presentation we did on the Astro Imaging channel last Sunday night. Rod Palmiere, he told us what they're like, what their shapes are. There are like 6 different classifications of them. Um, their role in cosmology, how they help decide how big the galaxy was, how their role in where the development of the galaxy, and all those important things. They're really interesting. I mean, Rod did a great job. He also told us a little bit about imaging since we're the Astro Imaging Channel, duh. But anyway, go back and here the URL is under that thing there. Okay. But it's the Astro Imaging Channel. It's pretty easy to find. Last Sunday's show. The next one we're looking at is Triangulum M33. The Triangulum galaxy is a spiral galaxy, and it's about 2.73 million light years from us. It's the 3rd largest galaxy in our local group. Altogether, it covers about twice the size of the moon. So imagine it's twice as big as the moon, apparently. It's bright enough to be observed in 10 by 50 binoculars, away from light pollution, of course. And with the telescope, you'll see a lot more of it. And we've got 2 more, I think. Or maybe we got 3 more, depending on how we count it. One of my favorite objects, or maybe 2 of my favorite objects, is the double cluster up here in Perseus. It's naked eye. You can look up in the sky and you can say, what's that fuzzy patch up there just next to the Cassiopeia? It's actually over in Perseus, but it's right up there. And when you put binoculars on it, or a telescope on it, or a camera on it, it just dazzles because it's got lots and lots and lots of pretty stars. It's about 7,500 light years away. And either of those star clusters would be really great objects, but together they're like double good, double good, double good. Triple good, maybe. I don't know. Lots of good. Did you go? There we go. And everybody's favorite this time of year is, of course, M31, the big Andromeda galaxy. This is the most distant visible object. In other words, the farthest thing away that you can see with your naked eyes. Cassiopeia has a certain structure, one part of the W of Cassiopeia points to it. And there are other ways to find it, but that's the way I always find it. And you look up on a dark night, and there it is. You put binoculars on it, and whoa, there it is. You put telescope on it, and you can't see it all because it's about 6 times the size of a full moon. Okay, so all those things are really cool. Now, there's one other slide I got to put in here. Every year we go down to Borrego Springs, and there's about 200 people. We've got an RV resort with hotels, spas, pools, and we fill it up with astronomers. This year, Molly Wakeling, who's one of the editors of Astronomy Magazine, will be there, and she's also on the Astro Imaging Channel with us. And she'll be doing a show on imaging, about how to automate your image and how to automate your processing. In addition, we've got about 8 or 10 other presentations. You're all welcome to come on down. Nightfallstarparty.com. It says, oh, actually, the URL does show up there. I got to tell you, they're all sold out. The hotel is sold out, but there's a campground half a mile up there, and there are hotels all over the place. And you don't have to register for Nightfall itself. You do have to register for Molly, because she costs $80 to sit there with her for 4 hours. But everybody else is invited to come on in and just hang around. There's a swap meet. There's a scorpion hunt. Although I got to tell you, as the weather cools, we don't find as many scorpions. But that's what's up. Thank you.
Thanks, Alex. That was really interesting and well presented. How many people are going to go to Nightfall already? 2, 3, 4. It's nice because it's warm, not hot. It's warm. You guys can shift over. You need the microphone. Okay, so we're going to switch computers and who knows what else, and I'm going to go quiet for a while. Okay, we're going to go on a 2-minute break. Okay.
share.
He wants to use the wireless microphone. It's over there.
Just the lights now.
You're gonna need to choose. And Zoom, please. On Zoom, I'm here on Zoom already. Okay. So you need to remove your sharing.
Oh, okay.
So you need to choose USB video as USB device, and audio as a USB device. And so
Mine's off.
Reza, do you hear me? Reza? Reza?
Yes, I can hear you,
Very good.
but I cannot see you. The presentation is also on.
That's yeah, that was the plan.
It's now in the presenter's mode.
Yep, it's all good. I'm ready. It's about the audience. If you prefer to be in the dark, it's good. I think that will be much better.
And if you could turn on your camera, and online we're seeing the presenter mode, not the actual presentation.
The actual presentation. Where is this? Reza? So
Yes.
I'm sharing the slides, right?
You're sharing the presenter's view of the slides. Right, you'll see multiple slides.
So it's that nonsense. Okay, this, I guess. So and guide me through. So I'm in Skype. What do I do? So I'm in presenter mode. In do I go to? It's there. So where do I go? Here. That's the presentation. And Reza doesn't see it.
Yeah, we saw the presenter's view side of things. Does it give you an option when you want to share your screen to share another thing, or
Sharing. Yeah, just a second, Reza.
So share,
Yeah.
and I do this, right? Maybe I share this desktop.
Yes.
And I think that should be much better. Do you see it right now?
Yes, perfect. We see this screen. Now, if you could just turn on the video, your video, that would be great. maybe I can send a request.
This camera up here.
Do we need this?
He wants to see you, so if you put in,
Okay, all right. So, sorry about this. I guess I am getting into, right. I'm going video, and,
the USB camera over here.
oh, well, I guess it's here, video here. I have to be able. Okay, I
Yeah.
do this and
That's you.
that's me. Okay, cool.
Excellent.
So, now I'm,
You're on this camera, so,
okay, I'm doing this.
which is okay. All
Are
right.
we good?
Yeah. very good.
Yes.
I don't count.
So, shall I begin? Okay, first of all, okay,
Reza, are you going to introduce Slava?
Yes. Shall I?
Yes, go right ahead.
Okay, so ladies and gentlemen, our speaker tonight at tonight's meeting is an astrophysicist at NASA's Jet Propulsion Laboratory and a professor at UCLA. He holds a PhD in quantum field theory and from Moscow State University. His groundbreaking research spans gravitational physics, space navigation, and exoplanet imaging using the solar gravitational lens. He has led key projects for NASA, including the ESA microscope mission, and has published over 220 papers. Please join me in welcoming Dr. Slava G. Torishev.
I'm going to go up and see the presentation.
absolutely, excellent. Thank you very much for Reza. Thank you for the presentation, and actually, I'm very happy to be here in this audience. Thank you for the invitation to speak with you about a very interesting project that we are now began development. So, with the realization that we are limited by observing capabilities, looking at exoplanets in the universe. We are not able to see those exoplanets directly. So we turn our attention to some very unique capabilities that nature offers us. So look at this wonderful slide. You see our own Earth with about 10,000 by 10,000 pixels. It's a composed image from taken by NASA Terra spacecraft. So we are, with the technology advancements, we became accustomed to seeing things in very high resolution. So we would like to see things that we cherish. We like to see pictures of favorite places, and we would like to be able to see the universe with the highest resolution. And looking at the fact that we discovered now many exoplanets, but traveling there probably will take us, our civilization maybe will travel there within 200 to 300 years from now. So, but can we do something before that? Can we see those exoplanets directly? And that's basically, this is what we'll be talking today about. And so just get ready for many different slides, different pictures, different statements. And so please don't shy, ask me questions right away, because if you don't ask those questions, they will be either forgotten, or basically we will get through the presentation and some basic concept will be missed. Because we'll be talking about general theory of relativity, we'll be talking about different telescopes, instruments, flight technology, and just ask me when you have any question. So with this, I would like to ask you, looking at this wonderful picture of our planet, how many of you think that there is life outside the Earth atmosphere? Just raise your hands. Wonderful. I agree with you. This is life. This is the life that we see. And this is wonderful life on the space station. These are my friends who are on the space station, in the cockpit of in one of the sort of areas in the space station. But is there life beyond the one that we know pretty well? So this is still us. This is still us. These are the humans who were born and live and come back to this planet. So, and the question is there life beyond just beyond this distance? And so with this, this is all coming back to our 6-year-old child within us. So remember yourself first seeing wonderful pictures of the universe and the stars, and you wonder if there is life out there. And
maybe someone out there is wondering what it's like here. Yes. Do you think we'll move them? So,
it's the question that we asked ourselves whether or not there is life in the universe beyond our planet. And basically, we as a 6-year-old, the inner child within us is always asking, is there anybody else? So, and Enrico Fermi said that if they're aliens, why haven't we seen them yet? And so, but with the new technologies and with the discoveries of many exoplanets, now we have a very different branch of astronomy, essentially exoplanets, studying exoplanets. It's a different zoo where different species live in different planets, different nature of those planets. It would be very interesting to understand when at what point we will find those planets that are similar to our own Earth. And this is why, driven by this idea, we started looking at something quite interesting. So today I will be talking with you about a direct imaging and spectroscopy of exoplanets using something which is quite unique, solar gravitational lens. It's the gift from nature that we'll be using to advance our understanding of the universe. And so this is the project that was funded by NASA within NASA Advanced Innovative Concept. And we have we went through multiple phases of this effort, from phase 1, phase 2, phase 3, and pretty much NASA invested into this investigations almost $3 million. So on the sort of duration of about 5 years, we have we went through different phases of the investigation. And this is a group of people who contributed to this investigation. Many organizations in the United States, here in California, and pretty much around US. And there are some European colleagues who are now joining us to actually, there is a realization that it's challenging, but feasible. It's feasible, and basically there are many people are joining us to trying to develop those technologies, trying to understand what and how can we actually build this mission that will bring the imaging of exoplanets to reality. Look at this interesting slide that actually describes the sort of brief history of solar system investigation. We were in around every planet in the solar system. We traveled to inner planet, outer planet. We've been at Mars multiple times. We traveled everywhere, and looking for life in the solar system. We know that beyond the Earth, there may be several places in the solar system where we will find primitive life. And I think looking at Mars, of course, we'll find probably the remnants of life that used to be there. And so the 2 satellites of Jupiter, we of course expect to see, to find something in the oceans of Europa and Ganymede around Jupiter. But I guess my favorite object is Enceladus around Saturn, because when Cassini spacecraft flew by Enceladus, it found geysers streaming off the south pole of Enceladus. And so geysers like water particles that were streaming outside the ice shelf. And that would be exciting to actually fly a spacecraft through those particles and to see and confirm whether or not we will find some organic life in those plumes emanating from the ocean of Enceladus. And I will be talking about the mission that we are studying on this, but not now, a little bit later. So, but beyond the solar system, in the solar system, looking for life, intelligent life. At one point, we were asking if life on this planet may be called intelligent, but nevertheless. So looking for life beyond the solar system. Of course, there are plenty of different opportunities, and we're looking at multiple stars within our galaxy. We know that there is still sort of star formation regions in the universe. We know that in our galaxy alone, pretty much about 50% of planets, stars have planets, and maybe between 1 to 10 planets. And we expect that there's some up to a few trillion planets in the Milky Way galaxy. And so there are many planets, and we just begun scraping the surface in discovering those exoplanets. The exoplanet discovery efforts are pretty recent. The first exoplanet was discovered in 1989, and since then, few decades only, and we were able to discover quite a few exoplanets. By now, we know that there is 5,800 of exoplanets confirmed. There are many more planetary candidates, more more than 10,000 planetary candidates. There, we know that planets are ubiquitous. There are many planetary systems, meaning that there is that some host stars have not just one planet but multiple planets, and we are now getting into the very interesting set of exoplanets which are terrestrial, meaning that they have solid surface, and so they started to resemble our own Earth, but we are not there yet, because the challenge is actually to find the planets that's similar to our Earth. It's very tiny, orbiting nearby the big star. And so how to discover those planets? I will be talking about technologies that we are using to do that. But it's quite exciting. The question about finding Earth 2.0 is not the question of if, it's the question of when. And we have multiple missions that we are building at NASA and the European Space Agency, essentially, that will be aiming to discover those exoplanets that are maybe planets similar to our own Earth. But before that, this is the map of our sort of neighborhood within 100 light years from us. And we see already quite a few exciting targets. I guess TRAPPIST would be one of interesting systems where we have multiple exoplanets orbiting the star. And so we have already coordinates of those exoplanets. At some point, this map will be very dense. We know that the planets out there, and the technology that we are developing will allow us to confirm that the exoplanets are orbiting around those stars. But the question, can we see them? Can we see those exoplanets? Look at the sort of statistics and the techniques that we're using to discover those exoplanets, because we are not able to see them directly. Because imagine the situation when you observe a firefly on the background of a searchlight. And so it's a very bright searchlight, and the firefly is very, very faint. And essentially what exoplanets do, they don't reflect light. They don't emit light, they just reflect light. And that reflected light is very tiny. So for us to be able to confirm the presence of that firefly around the searchlight, we are looking at something, a gravitational binding between the two of those objects. And essentially we see the wiggle that the star makes on the gravitational sort of influence of the planet orbiting it. And so we have multiple techniques. And one of the most productive technique is the transiting method, where the planet goes through the disk of that of the host star, and the brightness of the host star dims periodically, and that's how we are discovering the presence of exoplanets. And you see in this chart on the left, you see the many yellow circles confirming that indeed we were able to use this method quite successfully to discover quite a few exoplanets. Another method is radial velocity. Radial velocity is that exactly where the gravitational pull of the exoplanet makes the star moves in and out, closer to us and further away from us, because they both orbit with respect to their common center of mass. And essentially the velocity, the spectrum that we detect from the host star, we see that the star moves in and out, closer and away from us. And that's how we discover other planets, and see the blue circles is the radial velocity tool method. And if you sort of look at the axis and you see like 1 year on the horizontal axis is the days of the sort of the period of the orbital period of the planets. And if you try to see about 365 days, and you see and the vertical axis like one Earth planet, you see empty space. It's very difficult to get into this region. It's and so the techniques that we have, we just don't have yet a technology that is sensitive enough to discover the Earth-like exoplanets. We are getting there. We're trying to develop these techniques, but we are not just there yet. In terms of the telescopes that we have flown and will be flying soon, you see we have quite a successful fleet of telescopes at ground-based facilities. Of course, we're talking about the Hubble telescope. Spitzer was very successful. Kepler and TESS, they discovered TESS specifically discovered quite a few exoplanets. Now we have James Webb in space, and at some point we'll fly something. We fly Roman telescope, which will have coronagraph, and we'll be able to see those interesting exoplanets orbiting nearby stars. And at some point, we'll look at Habitable World Observatory. So this is the progression of technology that is looking forward to maybe about 15 years from now. Roman will be launched hopefully within this decade, and Habitable World Observatory maybe the next decade. So we're talking now about 15 to 20 years from now. if we using this technology that is we embracing. Usually we fly telescopes and in the solar system, and those telescopes usually are Earth orbiting on a Lagrange or in a Lagrange point. So this is what we have today. And so, but I will, as I go through through this sort of the discussion, you will understand that it's just not enough. Look at this. This is a wonderful selfie that Cassini spacecraft took of all of us. It's a Cassini spacecraft trained at camera back on Earth, and you see in July 19th, 2013, this is all of us. You and I and everybody on this planet sitting right on this tiny blue dot. So this is wonderful, wonderful selfie. And so, but to make images like that, to make pictures like that, you need a very good light amplification. So Cassini had camera, but it's just not enough to see Earth with high resolution. Another similar picture, you see Curiosity rover on Mars on January 31st, 2014, looking back on our planet. And in addition to light amplification, you also need to have resolution. And if you do this, if you have resolution, suddenly you see that Earth is not alone. There is a moon around Earth. So you need two parameters. You need to have light amplification and resolution. And looking at those comparative sizes and brightness, you see this tiny rock, third rock on the bottom. Essentially, this is our Earth. It's very tiny compared to the giant star nearby, the sun. And so I remember that firefly and the searchlight. That's the analogy, to find this tiny rock and be able to observe it on the background of this very bright light source. It's very challenging. So this is why we are able to detect quite a few exoplanets, but those exoplanets are with a direct imaging. We are looking at not Earths, we're looking at super Jupiters, and those super Jupiters were discovered. Look at those distances. We're talking about what it's 52 astronomical units away, and so we are not able to see inside of this area that is. Basically, it's a shaded area because we cannot look directly at the star, so we cannot look very close to the star. We are able to see the presence of those giant exoplanets that are orbiting host stars. We are not able to resolve them. It's a big blobs of light, not resolved light. So we know that it's a direct imaging. We are able now to detect super Jupiters orbiting their host stars at a very large distance. But remember, we need to find rocky planets at a very close orbit to their host star. So because rocky planet, those evolution of those planets will make the surface solid. So solid surface probably will bring some other interesting conditions. We will have oceans. We will have a stable orbit. But those giant gas planets, they're very difficult. I mean, we don't expect life to be present on those sort of giants. Will be very. We are looking at something that will be very close to the host star. And even we have flown James Webb, and the first images of James Webb that this telescope had taken, yes, we see the presence of exoplanets, and they're big exoplanets and orbiting their host stars at a very large distance. But with this 6.5 meter telescope, we are not able to resolve those planets. Let's put the numbers together. And we are sitting here in Orange County and essentially in Irvine. So for us to be able to resolve our own Earth at 100 light years away from us, still our neighborhood, it's very close, 100 light years only. So we need to have access to a telescope with 90 kilometers in diameter, single pixel. It's like diffraction limit. It's a tyranny of diffraction limit. To have image of that object, our own Earth, which is 100 light years away from us, it's still our neighborhood. I'm just repeating myself. To image that object, which is single pixel, you need to have access to a telescope of 90 kilometers. And basically 1.22 lambda over d times the distance. It's basically diffraction limit. So to have, if you want to image that object with multiple pictures, remember we looked at this beautiful image of our own Earth with 10,000 by 10,000 pixels. Multiply that number, 90 kilometers, by the desirable number of pixels you want. So that's basically how you estimate the size of the telescope. And look, it's very conveniently for us sitting here in Irvine, essentially, you see the diameter of the telescope, JPL, is right here, and it's up to Dana Point. So that's the size. It's almost 90 kilometers. It's 10 kilometers shy from the official boundary to space, right? So that's the size. And if in the future we will be able to build something like this, like it will be few atoms thick, and we'll be flying this foil into space and unfolding it, that object will be removed from the solar system by solar radiation pressure in just less than 1 year. So basically, it's like very hard to contemplate technologies that will be needed to build something like this. You may ask me, what if we'll fly interferometers? Interferometer will be, let's say, I fly 2 telescopes. Each of them will be 30 meters. And they will be separated by 2 astronomical units away, right? So like 1 EU orbit, and they basically, the 2 of those telescopes will be separated by 2 EU, and I have 2 30-meter telescopes. And I would like, if I will be imaging that Earth that is orbiting the sun, I would need to have coronagraphs to block the host star. So there will be star shades, essentially. I will have to fly 4 spacecraft. There will be 2 telescopes and 2 star shades. Then I would need to have a very large integration time to integrate over the exozodiacal light and all the exciting noise sources that will be there. So for me to reach signal to noise ratio of roughly 6 or 7, desirable detection like 6 or 7 SNR will be. So in this case, I need to integrate over 1 million years. Just digest the number. 90 kilometers and about 1 million years for an exaggerated system. 2 30-meter telescopes in space separated by large baseline, optical metrology, and even interferometer is not imaging. You're not imaged with interferometer. You need to rotate your baseline to cover your UV plane so that you will be able to make the image. It's only to resolve the diameter with 2 telescopes. So it's not really, imaging interferometer is wonderful, but it's not for the purpose we want to have it. So this technology is just not happening. And remember, we want to have something like this, right? So let's look at the history of telescope construction. Looking back about 100 light years, I'm sorry, about 100 years. So you see those wonderful telescopes that were built in 1948, Hale telescope. Then go through progression. The largest telescope we are building now, it's about 39 meters in Chile. It's European extremely large telescope, and it's not operational yet. On the bottom here, you see the impression of that telescope, how big it will be. Just for comparison, this is the car. It's not yet operational. It will be operational hopefully by 2028. So we're building another telescope, 30-meter telescope on Hawaii. So this is the state of our technology. We're talking about 30 to 40-meter telescope on the ground. And in space, of course, we have flown Hubble with its 2.5-meter telescope. We have flown now Webb, which is 6.5-meter telescope. It's just not happening fast enough to have the telescope that is big enough for us to start seeing those objects in our neighborhood with very high resolution. This is why we decided to look at something very exotic. And exotic in the sense we know that gravitation works very well in bending trajectories of light. According to general theory of relativity, when the light travels nearby a massive body, trajectory of that light is no longer a straight line. It actually bent towards that body. And so when we fly spacecraft in the solar system, anywhere on Mars, Mercury, Pluto, we routinely account for that light bending effect and Shapiro time delays. So those effects are very well known. And on the left, you see a big picture of microlensing events that we are seeing when it travels by the massive galaxies or star clusters. We understand that the formation of something called Einstein ring. And Einstein ring is formed when the light envelopes a massive body, and an observer which is situated on the optical axis on the opposite side will see those wonderful rings and arcs. And you see on this image, you see those wonderful arclets formed by the massive cluster in the center of that image. And so microlensing is a standard technique. We are using it to discover exoplanets, essentially extragalactic astronomy. We discover exoplanets orbiting stars in adjacent galaxies, not only in the Milky Way galaxy. So microlensing is a very strong tool. And the microlensing analytics is very well established. Modeling is very well understood. So essentially, it requires a very good alignment between the source, lens, and observer. And usually when we see those events which we see on this picture, it's those events which are happening with lenses which are, that are far away from us, they're happening on human time scales. So meaning the event would last very long usually. And so when the lens is nearby, event would go maybe like 20, 40 days, and then it will never come again. So in the solar system, we have the advantage that we can engineer that alignment. At JPL, we do it well. Essentially, once we know the source out there, and once we know the lens, and the lens is our sun, so we can actually draw a line from the source, from that exoplanet, through the center of the sun, and we can put a spacecraft on the other side of that line. And that's basically will be that alignment. And the spacecraft, when it looks back on the sun, it will see something that I discussed, the Einstein ring. And so I will talk about this. So that was the basic idea. And in fact, this idea, originally it was suggested by Professor von Eshelman in Stanford, and he was the PI in radio science experiment on Voyager 1, Voyager 2 missions. And he said that, why don't we use solar gravitational lensing to amplify light or actually radio signals emitted by different sources? And maybe somebody is out there who wants to communicate with us and maybe send us a signal or a microwave signal. We will use solar gravitational lens to amplify those signals. So von Eshelman did this in 1979. And then Claudio Maccone, an Italian scientist and engineer, picked up this idea, started thinking about flying a mission, and European Space Agency considered a mission called FOCAL. And so, but that was not sort of pursued. We realized that in our work, we realized that using radio waves is not very effective, because solar corona essentially causes those waves that are coming close to the sun to diverge, not to converge, but to diverge. And so essentially, because of the diffraction in the solar corona causes this light to diverge. And so we decided to focus on optical radiation. So a higher frequency or shorter wavelength. And essentially when light goes through solar corona, it's not being affected that much. So when light travels through the solar corona, we can actually benefit from the fact we understand how the trajectories of light, how light propagates. And I will talk about this. So this is, this led us to the very idea of developing the concept of solar gravitational lens. How this works? Imagine yourself sitting in a movie theater. Behind you, there is a projector. And in front of you, there is a screen. So when light that is emitted by a projector reaches the screen reflects light that goes back into retina and forms an image in your brain. That's how it works. Now, imagine the possibility that screen is not there. Screen is removed. The light field is still being projected by that projector, right? But there is no screen. How would you know what that projector projects? You go, as I am standing here, you go on stage, and you start moving step by step, pixel by pixel, looking back at the projector, and you record brightness of that projector. And so as you go through the image plane, X and Y, you record brightness in different pixels. Then if you know the properties of this projector, you can recover the image that this projector actually projects. So that's how gravitational lensing imaging works. So again, in the solar system, when the light is traveling nearby the sun, you see this, the sort of the schematics here. So when the light reflected by the exoplanet travels around the sun at some large distance away from the sun, unfortunately. So those rays that are enveloping the sun will start intersect. And essentially the lens, the gravitational field acts as a lens. But this is spherical aberration, so there is no single points, no single focal point. It's a semi-infinite focal line. So essentially, depending on the impact parameter, a light ray may actually intersect not closer to the sun, but a little bit further away. So it forms a focal region, where if you put a telescope there in that focal region, and you will look back at the sun, and usually when you buy a telescope, they usually tell you, don't look at the sun. In this case, you will be looking exactly back at the sun, and you will have something called coronagraph. Will just be blocking the solar brightness. And when you look at the sun, and if the exoplanet is bright enough, you will be able to see that light of exoplanet forming Einstein ring. And so that's the idea. you will be moving in the image plane, will be recording brightness of that Einstein ring. You don't have to resolve it, just basically recording brightness of it. And then moving pixel by pixel, recording the brightness, using the properties of the solar gravitational lens, its points per function, you can actually recover the image. And so, but thinking about this type of operations, if I use just a simple 1 micron wavelength, solar gravitational lens gives me amplification of 11 orders of magnitude. It's 10 to the 11th. That's where the beauty of it comes. So it's a ratio over the Schwarzschild parameter to the wavelength that I'm using. So 11 orders of magnitude for free, if you get there, right? So the light intersects, begin to intersect because sun is not letting the light go through. So essentially, those rays that are just sort of touching the surface of the sun, sort of only those rays will intersect somewhere at 548 astronomical units out. 548. That's the challenge. But then, if you go further, that image is still there because it's a semi-infinite focal line. And the image of our own Earth, if I put it at 100 light years away from us, the image of our own Earth, which has a diameter of roughly 13,000 kilometers, the image of that object will be formed within a cylinder with a diameter of 1.3 kilometers. 1.3 kilometers the diameter of that image. Now, if I take a 1 meter telescope and move with this within this light field, looking back, using my coronagraph and recording brightness of that Einstein ring that is formed around the sun, pixel by pixel, right? So I can, knowing the properties of the solar gravitational lens, I will be able to form an image. So that's the logic behind it. So what am I given here? I was given from nature by a light amplification, significant light amplification, also significant resolution. It's still lambda over d, but in this case, d is the diameter of the sun. It's not the telescope like 90 kilometers. I'm given a sub-nano arcsecond resolution. In this case, I'm talking about imaging that exa-Earth with the resolution on the surface of roughly 25 by 25 kilometers. Imagine the city of Los Angeles can be imaged within, I would say, what about 5 to 3 pixels. So that's city of New York will be imaged to what is maybe even a higher resolution because it's a larger footprint on the surface. So we're talking about now resolving continental lines, the topography, weather pattern. And so in addition to that, as you will see further, this lens provides you with amazing spectral capabilities. So you can now not only do the imaging, but also spectroscopy. And so let's talk about this. So the challenge, of course, is how to reach that distance. And in this slide, you see our stellar neighborhood all the way from our sun to Alpha Centauri. And conveniently, everything is placed in logarithmic scale, of course. So just appreciate how empty the space is. So there is nothing except Voyager 1, Voyager 2, and some other spacecraft. Voyager 1 today is at the distance of roughly 171 astronomical units out. It was launched in 1972, and essentially that spacecraft, so it's 74. So, but basically, it took almost, 40 years for the spacecraft to reach that distance. It moves very slow compared to the speed that we want. We need to go 3 or 4 times further. So, but that mission was built in 1970s. Today we can do better, and we can do lighter spacecraft. We can use different technology that actually will allow us to form and to use an sort of inflatable or deformable mirrors. So essentially, this technology will allow us to fly 1 meter telescope or telescopes in plural to that region. And this is what I will be talking about. So here you see essentially our solar system, the Kuiper Belt objects, Voyager 1, Voyager 2 is here. And in the middle of that image, conveniently in the middle, it's a solar gravitational lens region where you want to be to start imaging. And but looking at this, what do we do? Once we get there, it's just once we get there, we turn we put our telescopes pointing back at the sun, and around the sun, so we actually put a coronagraph, so we're blocking the solar light. And so suddenly you start seeing something that we discussed, Einstein ring. And moving within that ring, you will be able to sort of, when you put coronagraph, you block the sun. And so now you see the sort of the light coming from the Einstein ring. If you record the brightness of that Einstein ring, you're done. And so it's easier to say, but now what do we actually gain? So these are the simulations that we have done with full understanding of the properties of a solar gravitational lens. And so on the left, you see a typical image of our own planet, the Earth, and then we convolve that image with the point spread function of the solar gravitational lens. So you see that blurry image. This is our this is the image of any object that is produced by the solar gravitational lens. Remember, there is a spherical aberration. And so when you put our spacecraft in, this will be 1.3 kilometers by 1.3 kilometers image. So you put that spacecraft and you move it pixel by pixel, let's say maybe every 10 meters. You collect brightness, so maybe every 100 meters you collect brightness, and you start sort of deconvolving that image. You can actually form a pretty decent image of the Earth. You can you can completely remove the effect of the solar gravitational lens if there is no noise. If there is no noise in the data, then basically you're able to recover pretty decent image of the exoplanet. You're talking, this is an ideal case when there is no light noise taken into account. So we are not talking about solar corona here. We're just looking at the dark sun, only effect of gravity. So there is no radiation, only gravity. And in this case, you can actually talk about megapixel images. And so this is amazing. So if you have artificial, if you have a self-luminous sources, for example, you're looking at the quasars, if you're looking at something that is self-luminous, suddenly the solar corona and the solar brightness is not that important. You can use this solar gravitational lens to observe those self-luminous sources with very high resolution at very high brightness. So, but in this case, we're talking about very faint sources, the exoplanets. And so that actually creates challenge because sun is bright. So sun, of course, has a lot of brightness, and not the sun itself, but solar corona. Sun, we're blocking with the coronagraph. We don't ask for very demanding coronagraph. We're not talking about 10 to the minus 10, as typical coronagraphs that are building now for exoplanet hunting missions. We need only to block the sun, the solar brightness. We need 10 to the minus 7. It's still high, but it's more doable. It's more affordable. We know how to do this. We have simulated, we have built the technology. It's available now. So, but with this, looking at the solar corona, so essentially you see how solar corona behaves. If we are at the 548 astronomical units out, our rays are just touching the sun. So we don't want to observe Einstein ring that is just formed just around the sun immediately, because it's very difficult to resolve it, to remove it from solar brightness. We need to move a little bit further away. So starting from about 600 astronomical units, we start observing somewhere here. And our mission that we designed so actually allows us to go from 600 to about 900 AU. And so, but the solar corona produce a very significant noise at this distance. But it's not a problem. You know how to deal with that noise. And essentially, when you put every noise sources together, so when you put exozodiacal noise, when you put noise from the solar corona, what I'm showing here is a signal-to-noise ratio. If I'm dealing with the optical spectrum in the visible spectrum, let's say like from 0.4 to 0.9 microns. In this case, with the 1 meter telescope, with the integration time of 300 seconds per pixel, I can actually build that image with one telescope, assuming the planet is static, there is no diurnal rotation, there is nothing. I can build that image within 7 months. So, and I can build that image and I will be able to actually make an image of with very high resolution here. If I'm using a very different region, if I'm talking about a sort of near infrared, in this case I can use smaller telescope, and because in the near infrared the planets actually emit the light as well, because they're warm, and because they're warm they're emitting light, so its signal-to-noise ratio is very high. I can fly a very small telescope, let's say 70 centimeter, maybe actually up to 40 centimeter telescope. With the 40 centimeter telescope diameter, I will be able to reach very significant signal-to-noise ratio within 1 second. So that's an amazing promise of this technology. So what can I do with this type of technology? What can I do with this? And so if I'm accounting now for all the noise sources, and I understand that nothing is static in the universe, there is a proper motion involved because the host star moves with respect to the sun. There is a diurnal motion. The orbital motion of the exoplanet around the host star, the planet rotates. So if I account for all of that, these are the imaging capabilities I'm talking about. So for the planets that are very close to us, within, I would say, 3 parsec from us, are we still talking about megapixel imaging? So megapixel imaging is very impressive. Now you're talking about, let's say, 600 by 600 pixels image of exoplanet. And if we're talking about 100 light years away from us, which is 30 parsec, we're talking about 128 by 128. It's not as impressive, but look, it's incredible, still incredible. We are able to see a lot of things, a lot of details, and we are able to see whether or not there is water. Again, the topography, continental lines, if there's some lights, even those questions that we don't usually ask ourselves, what if there is some life on that exoplanet? We will be able to see day and night and structures on the surface of that exoplanet. And in addition to that, this is only visible range. If I'm talking about infrared, in infrared, I will be able to see a lot of details. I can do spectroscopy, and spectroscopy is very impressive because now with the spectroscopic capabilities, I can look for those oxygen, nitrogen, methane lines, and I will know exactly if there is a swamp. I can do spatially correlated spectroscopy. I can actually understand from what part of the continent that emission is happening. I will understand where the swamps are on that exoplanet because there will be significant emission of methane. If there is oxygen, nitrogen, I will know exactly where continental lines. I will be able to confirm that there is water on that planet. And also, if they use the same carbon fuel technology as we do, we also understand that those aliens who live there as unintelligent as us. So, but it will be some understanding how life evolves on those planets. Of course, I'm using those words with caution because we don't know what life is, right? So we don't know what to look for. We have never looked at ourselves, even understanding how can we remotely confirm the presence of life on exoplanet? What life is? How life can constitute. If you travel there, if you see life when you're there in situ, that's one thing. But how do you do this remotely? What constitutes life? We don't know that yet. We'll be trying to pose those questions and build telescopes and instruments that will be able to answer those questions. And so in this case, we are thinking that actually looking at multiple species in the atmosphere, we can look for methane, oxygen, nitrogen, carbon dioxide emission. We know which part of the spectrum we understand well and how those wavelengths emitted on our own planet. We will understand this well. If you do spectroscopy, we'll be able to confirm whether or not a life ongoing, if the planet is habitable or inhabited. There are two different things, right? How actually to pose those questions. This is what we are doing. So to fly a mission like this, we understand what technology we need to fly. We understand that how far do we need to go? Essentially, our mission plan that we have designed goes starts from science phase, starts from 650 AU, going all the way to 900 AU. The transit to that region, we need to go there fast because you want to do this within a lifetime of a scientist or engineer. So it's a very significant constraint, right? So we want to do this fast, and I will talk about how we'll do this. So we need to get there within 20-25 years. And essentially, we are flying several spacecraft because we need to be able to remove the cloud cover. We need to be able to get to understand how diurnal rotation influences the imaging. We need to have few of those spacecraft so that we'll have a cadence within 24, maybe to 48 hours. We'll be able to actually peek under the clouds to see what is happening there. So in essentially science phase duration, we're thinking about we will cover the distance within about 10 years. So it now gets to the point that the whole mission that we are building now, it's about 45 years in duration. We never built anything like this, but it pushes all the technologies that we know, pushes every pieces of technology so that we will be able to get there in reasonable time. And how do we get there? So now we just realized that we need to get there in a reasonable time, 20 to 25 years. We need to move fast. And moving fast is roughly 20 astronomical units per year. The fastest spacecraft that we have launched and we have today, it's Voyager 1, which goes which goes at the speed of roughly 3.1 AU per year. We need to go 7 times faster. How do we do that? What are the technologies available to take us that to those very impressive speeds? And so we understand that we looked at multiple of those technologies: chemical propulsion, of course, solar sailing, solar electric. We looked at nuclear propulsion, lots of different propulsion capabilities. We realized that solar sailing is the most promising technology. Now we have a lot of materials that allow us to actually fly close to the sun. So there is a crystal-based materials that allow us to reflect a lot of solar light. And so some of those materials are already available. Some of those are being designed at Caltech and UCLA, and we at some point will be able to demonstrate that in flight. And so solar sailing seems to be the technology that we would like to actually go with. So as I mentioned, we went through and we analyzed a number of those technologies, looking at the chemical propulsion. Even today, we fly wonderful Starship, right? So it's the biggest rocket we have, right? So with this rocket, we need to still go, there will be no direct flight. We still have to go back to Jupiter, get in gravity assist to Jupiter, fall onto the sun, and go by the sun, approaching the sun with very close proximity, do something called Oberth maneuver to kick us even faster. With this, we will be able to get about 15 AU per year. This is fast enough, it's good enough, but still not really, not very effective, because with this type of technology, it's a long duration in the solar system. You go in, you have to have thermal shielding when you go to the sun, Oberth maneuver, extra solid rocket motor. So it's a lot of complexities involved how to engineer a system like this. And you want to fly not one, but few of those spacecraft. So it will be expensive. And we don't want to build something that is really unaffordable. Solar thermal, nuclear electric sail. So all of those technologies have rather low technology readiness level. And so we realized that we need to go with the solar sailing, which is a basic technology. It's very simple. When you're on a sailboat, you have wind, you have sail, and you have a rudder. And in this case, you have solar radiation pressure. We're not talking about solar wind. It's very, very weak. Solar radiation pressure. And you have a sail, and you have reaction wheels, essentially. So it's a pretty much complete analogy with the sailboat. But in this case, slightly different, because I will talk about how to actually navigate things like this. What is happening when solar radiation pressure, when those solar photons impacting the solar foil, or the thin film that is used for sail purposes in the solar sail, there is momentum transfer. Momentum transfer sort of kicks that sail to very large velocity, and this is how we can actually achieve large speeds. We have built a JPL number of prototypes, and so I think the first sail mission we designed to fly to the Halley Comet, and I still have this picture when Carl Sagan is sitting in the Johnny Carson show and showing the biggest sailcraft that we designed in the 1980s. So back then technology was not there, because basically it was very heavy spacecraft. The reflective properties and thermal properties of the sails were not as we have them today. So now this becomes reality, because we fly small suns. We fly very light spacecraft, very capable, and electronic components now radiation hardened with a lot of productivity on board. So now missions like this are really feasible. So with this, what we have done, we're benefiting from 3 ongoing, very significant development in the space industry. First of all, we have demonstrated interplanetary small sats. If you remember Marco 1 and Marco 2, these two missions, two spacecraft were flown together with the Psyche lander on Mars. When Psyche was landing on the North Pole of Mars, Marco 1 and Marco 2 were 2 6U CubeSats were looking back in real time when the entry, descent, and landing on Mars, and they were able to communicate all the way from 2IU back to Earth. Tiny spacecraft, remember, 6U only. They were able to communicate and demonstrated that indeed you can actually develop very exciting capabilities with tiny spacecraft that we have today. And the cost of those missions, I think the Marco 1 was about 9 million, and the second Marco 2 was about 4 million. So the total mission cost of that was about 16 million. So this is, we paid it out of our internal money within JPL. So that's how we are pushing the envelope. So, but in addition to that, industry now develops a lot of different opportunities. And so now you can go buy those spacecraft and you can fly them anywhere in the solar system very inexpensively. So now, in addition, in another technology, the solar sail. If you see here on the left, you see mission flown by Japanese Space Agency. It's a JAXA. It's Icarus mission that actually flown all the way to Venus on a solar sailing. So not only did they use solar sailing for propulsion, they also have embedded photovoltaic elements on the surface of the sail, so that they were able to use sun directly to derive energy on board to drive electric propulsion. See the combination? And so if you can put phased arrays on that sail, you can use this for communication as well. You have a significant real estate on the sailcraft. Use it wisely. So not only propulsion, but also power generation, and use it for communication as well. So this is Light Sail 2 flown by Planetary Society here in Pasadena, was successfully deorbited only about a year ago. It's spent in space about 2 years, so was flying there. In addition, you see NanoSail D and NeoScout. Unfortunately, NeoScout didn't call home after it was deployed. So we are building those missions. We are developing now those solar sailing capabilities, because this is something that we would like to have. So thinking about this, in our work, what we have looked at, we looked not a planar sailcraft. We actually looked something with variable thrust sailcraft, because it's very difficult to navigate planar spacecraft. You need to have center of gravity translation. So center of gravity, center of pressure is very delicate. It's not that easy to navigate things like this. But with articulatable vanes, as you see here, it started with a company here in Tustin. So it's a Lagarde. So they developed something called Sun Vane. That was that idea in 2010. And then going forward, we started our effort with this type of articulatable vanes. At the wrist, they can be articulated. So essentially, very simple deployment. When you fly, it's everything determined by the length of the truss. So the vanes are folded. So during launch, when you're in space, the vanes are basically, you do this. You unfold once and you open the vane. So two deployments, each of the 6 vanes. And now you have motors that actually control the angle of those vanes. And now you have a fully capable sailcraft. And so the trajectory of that sailcraft you see here, in about 7 to 9 months, you're going very close to the sun. And then with this type of velocity, you already go into to a very high speed. So here we're talking about with the technology demonstration mission that I will be describing in a few slides down the road. We are aiming to achieve velocities of 5 to 7 AU per year, twice the Voyager speed. And so that is our technology demonstration mission. So we built actually a prototype, 1, 2, 3 prototype of that sailcraft. And you see, we are using, our idea was not to develop any technology. We don't need technology development. Buy everything that you can from the industry. So it's the aim was to reach area to mass ratio quite significant. The current area to mass ratio, the effectiveness of solar radiation pressure, the mechanism of transferring solar radiation pressure into acceleration, depends on a parameter area of the sailcraft to mass, total mass of the entire system ratio. So the typical sailcraft that we have flown in the past, see area to mass ratio of Icarus 1.3, very heavy sailcraft. And the Light Sail 1.3, NanoSail 2.2, 7.1 is NeoScout. So we're talking about area to mass ratio today, they're just under 10. We want to increase this 5 times. So essentially, with the lightweight structure, we don't have parasitic mass on the sailcraft. And essentially, the TDM would have to survive very close proximity to the sun, 0.2 AU. And so we are not asking for any technology development. All the materials are available now. So we actually have access to all of them. And so we use every possible sort of components, electronic components, Markov flown on Markov's spacecraft. And look at this mass. So only 6 kilograms total mass. And it actually has payload capabilities of roughly about kilogram. We're talking about TDM. We're not talking about the flight mission to solar gravitational lines. No, we are not there yet, of course. But we need to start flying to demonstrate the capability. It's like, for me, it's like a helicopter moment. Why I'm talking about helicopter moment? Because when we proposed to NASA to fly Ingenuity helicopter on Curiosity, So we were told, no, rotorcraft do not fly in the planetary atmospheres. So now after 57 flights that Ingenuity had done on Mars, now we are not thinking about exploring any other objects with atmospheres without rotorcraft. So that's what I'm saying, helicopter moment. You've proven your technology, and now you just build the capability into the exploration reality. That's we are waiting for the helicopter moment for solar sails. When we have flown one of those sails successfully, once we show it's navigable, and I'm using that word, it's not the proper English word, but it's navigable. You can control, you can navigate it, and you can actually deliver the spacecraft exactly where you want it to deliver. And they're not that simple. But once you demonstrate that, now people will start engineer this capability into their thinking, and that's very, very important. The cost of that mission, 19 million. So we are not talking about it's a private investments here. We can actually do this on private funding if a foundation interested in invest into this technology demonstration, it's like, remember Lindbergh Prize, right? So when Charles Lindbergh was flying all the way to Atlantic from United States to Europe, so there was a price set by a wealthy individual in New York who will fly there first and fastest. That's pretty much the same. We can fly spacecraft in the solar system, reaching the highest velocity at a very inexpensive cost. But that will push significantly on the capabilities for the community that we can have to fly things in the solar system. Now, that's the progression of our technology. See, we're now using something called diamond sails. Vanes, so that's sort of diamond-shaped vanes, and so essentially it's most effective way to actually fold the vanes. Again, it's a truss controlling the size of that structure. So once they're folded, it's the most effective way to do this. And so we actually built prototype of that vehicle. So that vehicle was built here again in Lagarde and Tustin. So we were able to build the whole vehicle here. And so using all the standard components, so it's 1 to 3 prototype. We moved it now into a showroom in a company called Explore in Seattle. So it's not only did we were able to build the spacecraft, we were able to disassemble, move it, assemble it again, and verify that indeed everything is operational. So that vehicle can be flown, and so, but the real vehicle that we would like to fly will be 3 times larger, and so that vehicle will go around the sun. So with this, how we want to achieve, so it's a launch profile for the technology demonstration mission. It's not the mission to the solar gravitational lens. So here, within about 7 months, we go through different phases of flight. We launch from right share, again, to save the cost. Then once we're in high Earth orbit, we deploy sail, we open the sail, start moving through different phases of the mission. Once we reach the orbit of Mercury, pretty much this is where the final checkup, and we dive into the sun and the solar proximity. And this is where, once we orient our sails, it's an elaborate Oberth maneuver. So essentially, when we're going by the sun with a very high velocity, we orient our sails to kick even larger, to provide even a larger kick to the sailcraft. That's how we do this. We studied the system extensively. So thermal insulation, we understand that it's important to keep thermal insulation. The vehicle will be in the solar proximity within about 27 hours. So we need to be able to see what will be the ambient temperatures around the sun. And so we realize that if you don't use normal thermal insulation, a lot of heat pockets. So when we use this the very standard paints on the sailcraft and using multi-layer insulation, the system behaves just beautifully at quarter of an AU. So right here. So we know how to build the system. We have tested it in the vacuum chamber. We know how things actually can be done. We actually vibrational tested the structure. It actually survives the launch loads. So surprisingly, those vehicles are very robust. You can actually fly things now. And so that's how the sort of the technology demonstration mission, the summary looks like. This is what we are now aiming to fly, maybe first around the moon, to demonstrate the maneuverability around the moon, very low altitudes around the moon, but then actually go all the way to the sun with this vehicle pretty soon. So that's this prototype now sits in Explore showroom, clean room up in Seattle. If you travel to Seattle, Washington, just stop by Explore, see this vehicle. But that opens a very different paradigm. With this type of vehicle, we can start exploring solar system much faster at a very different cadence. Just think about this. For the last 40 years, we had only 7 spacecraft that were beyond the orbit of Jupiter. Only that few. So you name them: Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, Cassini, Galileo, New Horizons. So these are the spacecraft. So it's a very sobering reality. If today's graduate from reputable university, so she graduates from Campton University here, and so she gets her PhD, and after getting her PhD, she's getting into one of the teams in the industry, be it at JPL, be it at the MIT, be it anywhere. So basically, the team will write first proposal. First proposal usually fails. Basically, you have to work. Second, pretty much you get a very good high scores, and it fails as well. So in the third proposal, your team will actually be given the funding to actually fly something that they're planning for. By the age of 50, she will see her instrument on the launch pad in the launch vehicle. Just that's reality, right? So the whole life of a young scientist goes for 1 or maybe two missions. It's not right. So with this type of capabilities, we can fly faster and inexpensive missions. So for example, if you look at multiple uses of this technology, and so this is all summarized in the paper that we just recently published. Now we actually bring in some additional funding to fly things like this. What I'm talking about, one of those missions I'd like to fly first. Again, my objective is to develop technology that will be needed to fly to the solar gravitational lens, something called solar polar imager. If you remember, when Cassini spacecraft had flown around Saturn, you saw that polar regions of Saturn have exhibited their hexagonal structure. There is a hexagonal structure because of the viscosity of the gas in those under those regions, and also rotation of the planet. You have a hexagonal structure on north and south pole of Saturn. Similar structure was seen by Galileo spacecraft when it was orbiting Jupiter. Now we expect Sun will have the same. Would it be fun to see those hexagonal structure on polar regions of the Sun? And so we have done something like this with Ulysses spacecraft. European Space Agency have flown this spacecraft. Spacecraft went all the way to Jupiter and then formed the trajectory, peaked at about 70 degrees solar latitudes, and that's all. We have not been close around the Sun. We have not seen the Sun. And so heliophysics community will be ecstatic to fly something like this. But to do this with chemical propulsion, again, you need to go all the way to Jupiter, get a gravitational assist, and then dive into the inner solar system. With solar sailing, we can crank the inclination about 3 degrees every 21 days. So we have studied this trajectory. Now within the, because solar sailing, you can form missions pretty much outside the ecliptic plane. You can fly not only the ecliptic plane, but you can actually start cranking the inclination. You start being polar within about 7 months, 8 months, you are completely polar. And at a cost of roughly 25 million, 27 million per spacecraft, you can fly several of them and monitor the solar behavior pretty much constantly. So that's one of the missions that we are developing. Another mission that is quite interesting is to look at our own planet as an exoplanet. Remember, I mentioned the transit method that we use to discover atmospheres of exoplanets. What if we look at the Earth transiting the Sun? And we use the same technology that we deploy to look at the transiting exoplanets to confirm chemical composition of atmospheres. Can we detect life on our planet by using the same technology that we use to look for life out there? So that will be a nice confirmation. But for that, you need to fly about 40 lunar distances away from Earth. And solar sailing can hover, provide you sort of hovering capability. You will be observing how Earth is transiting the Sun. And that's with chemical propulsion, it will be very difficult to achieve this type of trajectory. And so you can do not only Earth, but you can do also Venus, you can do Mercury. So now will become a comparative planetology. So now we will be able to see what actually constitutes life, how atmospheric behavior is changing if you look from one target to another. Another, my favorite mission is the next step would be going through the plumes of Enceladus. And so when you fly around the Sun, and if you now have a very capable system, you go through the plumes, maybe not with one spacecraft, but with several of them. One will be communication node, another will be diving in, will be taking the data, transmitting data through the nodes, going all the way to back to Earth. That would be wonderful. And so, but for me, my ultimate objective here is to develop technologies that are needed to fly for the solar gravitational lens. So what we are doing now, We were able to confirm that indeed you can actually form an image of exoplanet. You can image exoplanets with solar gravitational lens. Not only we confirmed that we actually can use that to our advantage, not only to image, but also to do very high spectroscopic studies of the atmospheres of those exoplanets. We have the mission design. We know how to compensate for planetary motion, for rotation. I'm not going through the details here, but I'm giving you impressions. So we are ready to fly. But we need to raise technology readiness level, and so to be able to actually to fly this mission by the time we're aiming about 2034. And so people are saying usually, look, to get there, you either need to move fast or live longer. And I prefer to do both. And I assume everybody in this room joins me in this. So we need to move fast and live longer in this case. But the point is, with technology that we have today, we are pretty confident we can fly this mission about 2034. And so, but again, it takes about 20 years to reach that region. So by the year of 2063, we will be able to see this, to form direct images of exoplanets. You will ask me, is there alternative technology? I doubt. So reality is that we can build larger telescopes, we can build different systems, but reality is that direct imaging of exoplanets is not reality within any classical concept. So that's the only way. And so, but to fly something like this, we need to improve technologies pretty much everywhere that we actually we have. So propulsion, communication, optical communication, power systems on a spacecraft. We're pushing pretty much every boundary here, and we know how to do things. But I guess one of the most important kind of realization is that it's a long-term project. We have never done anything that is longer, let's say 5 to 7 years. And here, this project will be about a few decades. In the history of humanity, we have flown only, we have done only a few of those big projects. What comes to mind? Great Wall of China, Pyramids of Egypt, Space Station. So it's a multi-generational project. So it's changing the paradigm how we do business in space, but it's actually very good motivation. So on this note, thank you very much. I hope at some point we will be able to sit here in this audience and see the planet, see the images of nearby exoplanets with very high resolution. At least this technology promising us to do that. So thank you very much. I guess, Reza, if there are questions, I would be happy to answer. Yeah, the question was about coronal mass ejection as we are going through the very close solar proximity. And so we looked at the anisotropic emission, we looked at the very sort of unusual solar behavior. And so we realized that solar sails are rather robust against those. So, and with the processing on board, we will be able to compensate for those. So it's not really, initially, I was worried about that. So now, as we will be sensing the environment on in this region, if thermally we are okay, everything dynamically we are totally okay. So we will be able to move. And plus, those events are not happening with very drastic emission. It's only when we see the imaging of those, you know, the sort of the images that we see on those. Reality, the dynamic environment near the sun is not very drastically changed. So I think we'll be fine.
Let's find out what Reza wants to do, and maybe you can answer questions live here, and we'll go off the internet. Okay. Reza, this is Doug. We'll sign off here and answer local questions unless there's stuff you want to ask.
There is a question online. Shall we ask it, or do we have time?
We should close shop pretty soon, but go ahead. We haven't been able to do that yet.
So the question is, what is the largest aperture you have considered?
For this type of mission, we looked at the 1 meter aperture. And so we can actually form 5 meter apertures as well. And 5 meter aperture will be, of course, very interesting to fly. But being realistic, we need to be able to sort of constrain our ambition here. Usually, when we talk about, usually when I'm asking students like question, just name 3 most abundant elements in the universe. And okay, of course. So Yes, thank you. So usually I'm asking my questions on lectures. Give me, name me the three most abundant elements in the universe. Anybody? I love those. You are right, but there was a trick question, of course. The three most abundant elements are unobtainium, non-existium, and anaphordium. So we are trying to stay away from all those three elements when we design missions. The question was, how do you stop the solar sail when it gets to the focal region? Because it is it's not a focal point. It's a semi-infinite focal line. You don't stop. You just continue going around that optical axis. So essentially, we are not stopping. Once we reach, we begin our science campaign and we continue moving. And we're moving with this light field that is being moved around. So it's not static. It moves because or the orbit because the planet moves around its host star, and even the sun is not static because it moves with respect to solar system barycentric frame, right? So it moves quite drastically. So if our system is designed to compensate for the largest motion, which is due to the solar motion with respect to solar system barycentric frame, once we do that, we are totally in business, and we know how to do this. It requires only 6 micron per second to move the spacecraft with this. So, but everything else we accounted for, we don't stop. We just continue coasting along that focal line. Reza, any questions online?
Yeah, one more question online, and that's you mentioned when you were talking about how difficult it is to image things of this size. Multiple times you mentioned pixels. So what is the size of the pixels that you're talking about?
You nominally you have this, let's say, 1.3 by kilometers diameter image. So the more data you take from that image, and if the data is uniformly sort of taken from that light field, you get a very good sort of image to start with. But the denser you cover that image, the better resolution will be. So it's really the question is, we are considering moving, let's say, 10 by 10 meters, and then putting a spacecraft within 10 meters with the steps of 10 to 100 meters. And then basically we put in the spacecraft, we're stopping it, and we're collecting data. And so that will form that sort of enough information for us to recover the full image. Because it's a spherical aberration, you don't really have to, I mean, within 1 pixel, you have information from adjacent pixels as well. I don't have time to go through technical details, but basically, let's say every 100 meters, you stop, collect data, and that will be enough to recover good image.
Thank you.
Questions here? How far from the sun becomes ineffective. And so essentially for the solar radiation propulsion, we were considering dropping sails anywhere after 3 AU. So once you get 3 AU, the solar radiation is not as effective. The biggest kick you get within, let's say, 1 AU. Of course, the closer you get, the largest velocity you gain when you're very close. So, but you can drop the sails, maybe part of the sails once you reach 3 AU. Yes. This is the question was how actually you can correct the orbit insertion errors as you injected from the significant acceleration phase from the solar radiation propulsion. So in this case, we have ion thrusters and we have electric propulsion on board. And so EP will help us to nudge us just a little bit, and we have long time of flight. We can always compensate for those errors. It's not that significant. So we can tolerate significant errors at the beginning, and those errors will be compensated during the flight. See, we have the Z component very significant, but X and Y component of velocity, we can still move with an X and Y with electric propulsion. That's the main idea. It's usually, now it's aluminized Kapton, And so this material being routinely produced in laboratories, you can fly, it's for the TDM, but there are some crystals that are being developed at Caltech and UCLA. Those crystals very lightweight, very reflective, and not very thermally, sort of not absorb a lot of heat. So those crystal-based materials are already being developed.
We're going to take the rest of the questions personally in here. So we'll bring the meeting to a close, and you can come up and ask more questions. It's really fascinating to get somebody with so much knowledge of an interesting subject and not be able to explore it completely. So we can do that way. Reza, we'll close off here. Is that okay?
Sure, all
Okay.
good.
All right, good. Nice meeting, and thank you very much. And we'll see you guys all in November, if not earlier.
Sure. Bye-bye, everybody.